Okay, I thought I would show you something else that's pretty cool we can do with mole ratios. I've written up under this video the definition of what an empirical formula is, but all it is simply just the lowest ratio of elements. So a lot of times in lab, if you've created some new compound, the best you can do is kind of figure out the ratio of elements that exist in a compound. We've been working with so far what's called a molecular compound, which is the actual formula. An empirical formula is the lowest ratio of elements that exist in the compound. So for an example, I've kind of given out these 5 different compounds. H2O, are we able to reduce that down any further? Nope. So that is the formula for water. That's the molecular formula for water, but that's also an empirical formula. It's the lowest ratio of elements that exist in that compound. If we look at the next one, N2O4, can we reduce that down any further? We can, and that would give us NO2. So the empirical formula would be NO2 for this molecular formula, the N2O4. Next one, I've got the formula for glucose, C6H12O6. We can reduce that down even further to CH6O. Wait, did I screw that up? I screwed that up. It should be CH2O. Oh, it took me too long to animate this, so I'm just going to go with it. Sorry. CH2O is what the empirical formula should be. Great. Next one, hydrogen peroxide, H2O2. We can reduce that down to HO. That's the empirical formula, lowest ratio of elements. And then methane, CH4, we can't really reduce that down any further. So that's both an empirical and a molecular formula. So like I said, working in a lab, a lot of times the best you can come up with is an empirical formula. So let's look at an example of what that looks like. I know some of you are step people where it helps to have steps. I've listed them here. But I know since we started talking about moles in class that my kind of new catchphrase was that everything in chem is a ratio of moles. And so in an empirical formula, it's just a ratio of moles. So if we looked at a problem, let's say you figured out that a compound that you had created was 41.9% sodium, 19.1% phosphorus, and 38.9% oxygen. Since we know everything needs to be a ratio of moles, let's turn it into moles. So let's assume that we have 100 grams of each of this whole compound. If we have 100 grams, that means I have 41.9 grams of sodium, 19.1 grams of phosphorus, and 38.9 grams of oxygen. And since everything's a ratio of moles, our first step is to put those numbers over 1 and then use the molar masses to turn it into moles. So I listed everything off here, and I get the number of moles present for each of the elements that are there. I do want to point out, if you look at the oxygen at the bottom of the screen, oxygen I have as just being monatomic. We know it's diatomic when it's by itself, but here it's in a compound with sodium and phosphorus. So I left it just as oxygen. So now since it's a ratio of moles, to figure out the ratio of everything in this compound, I'm going to divide each moles by the amount or the element that we have the least of. And so in this problem, that would be phosphorus. So if I divide each of them by the moles of phosphorus, it gives me the amount of the element per 1 phosphorus. So for every 1 phosphorus, I get about 3 moles of sodium. And then for every 1 phosphorus, I get 1 phosphorus, so that makes sense. And then for every 1 phosphorus, I have about 4 moles of oxygen. So if I piece this all together, the compound that I made in the lab was sodium phosphate. For every 1 phosphorus, there's 3 sodiums. And for every 1 phosphorus, there's 4 oxygens. Fun? Totally fun. Great. Here's another example. I'm not going to work through this. I'm going to leave this to you to try to figure out. But let's say I had a compound that was 82.8% carbon and 17.2% hydrogen. Pause the video and see if you can go from grams to moles and then divide the moles by the least amount that you have to find the ratio. And then we've paused, you've tried it. I got this as the answer, CH2.5. But wait, can you have 2.5 of an element? You can't. So to fix that, I'm going to divide the whole compound by, or not divide, I'm going to multiply the whole compound by 2. And then that gives me here C2H5 as the actual formula. We all right? Okay, so let's say that the actual compound that I made, knowing that I had this C2H5, let's say that the actual compound that I made in the lab had a mass of 58.0 grams per mole. I can figure out the actual compound by looking at the scale factor between the empirical formula and the molecular formula. So what I do is I took what the actual molar mass is, which is 58, and I divided it by the molar mass of that C2H5 that I had on the last slide. And that gave me the scale factor. Do you see how it's about double? The actual molar mass is about double the empirical, the lowest ratio molar mass. So to figure out the actual compound, I'm simply going to take that formula I had on the last screen, C2H5, and I'm going to multiply it by that scale factor, by 2. Okay, I'm going to give you a couple more problems, probably on Class Kick or some other format on Canvas, and then I want you to try this. This is what our homework is on. Again, feel free to get in touch with me if you have any questions.